Good morning, everybody. Thanks for joining us today. So the topic is hydrogen sulfide and its occurrence in a variety of environments that many of you work in across North America and around the world. And really part of this presentation is all about a safety shared with you. My observation working in the H2S file over a number of years is that it's almost out of sight, out of mind, but not out of danger. As I look through trying to determine where are the design standards, for example, that we would use for designing a system to deal with or prevent or deal with H2S occurrence, I find that a lot of the design standards, some of them went out of print long before the internet even. And so it's a topic that is worth refreshing from time to time. I know almost everybody on the call has gone through an H2S Alive program at some point in time. And so my presentation is going to focus a little bit more on what are some of the circumstances and conditions that you could find in, what are some of the things to watch out for regarding the potential occurrence of H2S, how would we detect it, and what are some of the management systems and due diligence requirements that we should follow. Joe, at this point, I just want to do a sound check, make sure that I'm coming across fine.
Yeah, all is good.
So H2S is pretty common. Many of you know it as perhaps around the world, maybe 25% of natural gas production around the world has some form of H2S in that production. So it's definitely something that we commonly associate it with oil and gas production. Some of you may remember some of the controversy years ago as the city of Calgary was expanding its boundaries and starting to encroach on areas in which there was sour gas production, and some of the controversy around the safety of that expansion into some of the areas surrounding Calgary. It's in the more municipal, mundane mining type applications. It is a byproduct of anaerobic digestion. And so you'll get sulfates that would occur naturally combined with some carbon and bacteria, and specifically sulfate reducing bacteria will generate both carbon dioxide as well as H2S. So in a sewer system, for example, basically that H2S that goes into the headspace in a sewer can be absorbed once again into the slime around the crown of the pipe. So it's a slime or it's a wetted layer. And in that circumstance, there's sulfur oxidizing bacteria that now take that H2S and convert it to sulfuric acid. And so that's why in a lot of municipal systems, or in some municipal systems, you'll find a fair amount of degradation of concrete piping because of the reaction of that sulfuric acid with the boundary layers on the concrete piping. And so there's a cycle that is involved in what happens to sulfur, whether it starts as a sulfate or ultimately ends up in a sulfuric acid. Is an active system or a live system that you'll often find in wet environments with organic matter. And so you might find it in sewers or silos or sumps, pits, ponds, mine adits, landfills, oil sands deposits, manure piles. So there's a wide variety of places that you might find H2S. So I took a look at the last number of years worth of incidents reported throughout North America, and fatalities in particular around H2S, to give you sort of an idea as to where it might occur. And so you see it doesn't really discriminate against a specific industry. So it can be found in agricultural or farming operations. It can be found within industrial operations. It can be found in rendering applications. They very commonly found in sewer applications, whether it's trenching, whether it's servicing, cleaning, obviously found in gas plant environments. There have been fatalities that have occurred just in restaurant operations where staff went down to clean out a sewer from a restaurant that was being problematic. You can see it in a variety of like tannery operations and that type of thing. So I'm not going to dwell on this list. And when you see the presentation in PDF, you'll get a sense that H2S doesn't really discriminate against a specific industry. So Hendrickson in 2004 did an assessment of about 7 years worth of reporting. So it was not just fatalities. Now, if I just go back to my list here, this is over the last 5 or 6 years in North America. Hendrickson did a pretty comprehensive analysis back and published it in 2004. So he looked at 7 years of data. And of course, in here are some lessons learned for us. So 50% of the fatalities, I think it was 48 or almost 50%, really were employees in their first year of employment. And all of us know, as part of a comprehensive safety program, that the most dangerous time is for safety is a new employee performing a new task. So the fatalities were most common in waste management and natural gas processing. Poisoning was most common in sewerage, as well as more downstream in petroleum manufacturing. And again, it doesn't really, at the time, it didn't really look like it was biased towards a particular size of company. So even larger companies had a fairly high fatality rate compared to smaller companies. So it sort of highlights the importance of not making an assumption that if you're a particular size of company and you have a particular program that you can be immune to the risk associated with poisoning from H2S. So some of the important physical properties, and I'm sure there's a couple chemists on the call, and so that understand this as better than I, but it's colorless, it is flammable, and it's highly toxic. And it's, of course, denser than air. So you remember from your H2S Alive lessons about where don't head downwind, downhill in the event of a release or an alarm. So it's very important to understand that because of that density, it's really affected not only by where it's generated, but it's also very much affected by wind speed, changes in barometric pressure, and changes in the configuration of the workplace. So some of the mining fatalities, if you go on the web and you scan some of the fatalities that have occurred, you'll see circumstances in which workers have gone into mine adits, confirmed that there was not an H2S risk, but during the time period that they were in that workspace, there would be a shift in the barometric pressure, a shift in the weather, and now you get H2S gas flushing through an area that had tested previously clean. So it's very important to understand the impact of denser than air and how it can mean a change in the H2S levels within a particular workplace. It is flammable and explosive at certain concentrations. So have to be very much aware of that. And of course, finally, solubility is also affected by changes in water temperature and pH. One interesting fact, when you look at how the state that you're going to find hydrogen sulfide, it's either as a dissolved hydrogen sulfide ion or a dissolved gas. And so you'll see over this range, this is kind of an interesting illustration of over the range. Joe, can you see my arrow?
Yes, we can.
Yeah, very good. So you'll see that in a very acidic environment, you have dissolved H2S. And so as the pH rises to a more basic or alkaline environment, you'll see the shift in the concentration to hydrogen sulfide ion. So that affects whether at lower pH, maybe you're trying to remove it, you're trying to bubble it out as a dissolved gas, whereas at a higher pH, you might have to be treating it for the HS ion and use some chemistry. So really, it's important to understand that over a narrow range of pH, you might get quite a change in the behavior and availability of hydrogen sulfide. So the availability of hydrogen sulfide, if it's a dissolved H2S gas in water, as we saw on this graph, at a lower pH, you get more H2S dissolved. That means at a lower pH, if the water is turbulent, then you might get more bubbling of H2S, making it available. Now, lowering the temperature increases the solubility. So a low temperature wastewater flow would have more milligrams of H2S available than at a higher temperature. And then finally, the turbulence of a flow really affects the amount of H2S that can be released. So remember, I talked about one of the industry standards for design, and I'm just opening up the book right now, and it's basically 1989, ASCE produced a manual for sulfide and wastewater collection and treatment systems. And so I've excerpted from there an example of some of the types of flow that could cause the turbulence and accelerate the release of H2S. And so you'll see a variety of configurations. These are biased towards sewerage type applications. But if you look at any industrial piping system, you'll see situations like this can also occur. And so if you have drop structures coming from a process wastewater, or you've got merging flows, all of those create conditions in which you might get H2S release. And so there's been some good work done and research done, for example, in the city of Edmonton around the impact of major drop structures on the availability of H2S coming out of the water and into the headspace. So it's worthwhile thinking about what are the various action levels that might be in place that are important for the protection of infrastructure, protection of worker safety, and protection of the public. H2S can be detected at a pretty low level. And I remember working at the Edmonton composter when we had basically a system, a biobed system, and sort of a bacterial system outside to treat trace levels of H2S that were coming out of the composting operation. And what we used to detect it was an odor panel, because we found people that could detect levels of H2S at levels that were below what you could measure analytically. And so you can get an offensive smell at a concentration as low as 0.5 part per billion. So that factors into how much of a risk is there if you have an H2S issue. What's the risk of it becoming offensive and creating a problem for your neighbor or your worker? So always remember that the detection levels are very low. And that's a good thing, because of course the mortality associated with higher levels of H2S is extremely high. And so it's good that some can detect it at a level so low that you can barely measure it through an analytical process. What you'll find in the sewer bylaws across North America are two ways that it's handled. It's either a prohibited, well, normally it's both actually. It's either a prohibited substance in the water or in the air, or a restricted substance in the water that's being discharged. And so it's prohibited as H2S because it represents a health and safety problem, in addition to a problem for the infrastructure. Sulfide levels are restricted because, as we talked about before, there are biological processes going on in the sewer that might convert a dissolved sulfide into H2S. And so it's important to understand that that's in most bylaw systems in North America. You've got both a prohibition of discharging any of it into the headspace especially, and a restriction involving the discharge into liquid effluent. So now we look at the hierarchy and what happens, what are the triggers at higher levels. So the American Conference of Governmental Industrial Hygienists basically sets two types of limits. One is an 8-hour threshold limit value recommended of 1 ppm, as well as a 15-minute short-term exposure. So in other words, if you're always below the 1 ppm, but in the day you have a 15-minute short-term exposure, then basically that's when you would evacuate and take precautions in that workspace. What's interesting is that QP, and some of you definitely have a workforce that is represented to some degree by the Union of Public Employees, and so QP recommends the adoption of the threshold values from ACGIH. Now within Alberta, we have the OH&S regulation 87/2009, and so you'll see a different level for exposure. You'll see the 8-hour level at 10 ppm and a 15-minute ceiling at 15. So it's important to understand that as you start to get up to different levels, there'll be different sensitivity depending on which standard you're using as to whether you would accept a lower level of, say, 1 ppm as your trigger, or whether you would go to 10 ppm according to the Alberta regulation. Now, what's interesting is you go to, as soon as you get to 50 ppm, so this is not a high concentration, you start to get irritation. The guidelines for an immediate danger to life or health is 100 ppm. And if you get as high as 1,000 ppm, well, then you will suffer from cardiac arrest, and of course, if not resuscitated, possibly death. So there is a fairly serious consequence as soon as you start getting up above the 10 ppm level. So irregardless of the level that's specified in the regulations, you have to be very alert to any circumstances that could cause the levels to go up as high as 50, 100, or higher. And I've seen applications in certain industrial areas where the levels can be over 1,000 going into a sort of confined space. And so definitely this is something to keep in mind as you're looking at your potential risks. So the key considerations for safety are make sure you identify the potential sources, especially organic or anaerobic digestion of organic matter. Think about the downstream conditions that can affect the state of H2S. So for example, you have a digester discharge at a certain concentration of H2S and a certain equilibrium between the hydrogen sulfide ion versus the dissolved gas phase. And then you blend that stream with, say, a boiler blowdown of a varying pH. Make sure you understand that how that changes the availability of H2S. Also understand how upset conditions can disturb the equilibrium of the system. Make sure you have adequate detection. Now, whether that's the workers with a portable device that they're using before they enter into a space that has the potential for having H2S in it, or online real-time monitors with alarms as well. So making a selection of the right detection equipment. And then, of course, and again, I'm preaching to the choir for many of you, the combination of engineering controls to prevent it from being generated. And that can be treatment associated with for example, your wastewater treatment plant. And then also adopting the operating protocols so that you respond immediately to any circumstance in which there's an elevated H2S, especially with the potential for any worker exposure. So the treatment options, moving on, really depend on your desired outcome. Are you focused on meeting effluent discharge criteria? So in other words, are you focused on achieving a bylaw, either a restriction or a prohibition? Are you worried about odor generation? I remember decades ago doing some air quality monitoring on one of the large regional wastewater lines because we were detecting odor in a regional line that was coming from one of the surrounding communities in the Calgary region. Is it an occupational health and safety criteria that you're trying to achieve? And then finally, are you looking at the H2S control to prevent any damage to infrastructure, especially corrosion and degradation of piping systems? And so when it comes time to choosing the treatment technology, you have a variety of options. You can do physical and mechanical. So in other words, if I've got H2S at a certain pH in a bubble form or dissolved form, am I going to go to some sort of physical process to get those bubbles out? Or am I going to go to a chemical process where I would add an oxidant of some type in order to get the H2S out? Or do I go to a biological process? Remember I talked about a few minutes ago, we used a biological process in the composter in Edmonton to take out any of the odorous compounds. So they were low concentration, but nonetheless still detectable by our odor panel. Or is it a combination of those three other processes? Thankfully, I'm not going to go through all of these in a lot of detail on this call. But you can see there are a variety or family of treatment technologies that really are based on whether there's a high volume of flow, whether it's a water or air media that you're trying to treat, or whether there's a low volume of flow. And there are some examples that have been quite commonly shared around Western Canada. I can't recall, I haven't seen the participants list as to whether there's anybody from Apache and Encana, for example, on the call. But an example of a conventional stripper is the DeBolt water treatment plant in northern British Columbia that was in place to remove H2S from formation water to make that water available for reuse in hydraulic fracturing operations. So that's an example of a type of technology that's really a physical combined with chemical process. So there's a family of technologies that are available, and many of these used, or all of these used in Western North America. So the selection really comes down to an understanding of the chemistry, volumes, and the ultimate performance target. Some of the performance targets also relate to the perception of the end user. So in looking at, for example, hydraulic fracturing water reuse applications, the service providers for the fracturing operations want to see H2S reduced to almost a non-detect level, and partly because of the concern around the perception of safety, and partly because of the need to protect the tubulars and equipment from any corrosion resulting from either an over or under treatment of the H2S problem. If you go to some of the lower volume systems, and this is something that many of you that are in the municipal sector would be familiar with, you can go to a variety of technologies and chemistry. So chlorine dioxide, sodium nitrate, iron sponge, carbon absorption, for example, is a good example of what's being used in some workspaces where you get only odorous levels of H2S and not higher levels of H2S, scrubbing systems as well. So you have a family of technologies and no single recipe or silver bullet around which technology would be applied. I want to share with you some of the systems and the variety of systems that have been used. So for example, I was lucky enough I was lucky enough to be involved in the Beverly Hills water treatment plant. Unlucky that I'm not still living somewhere in that area, especially now that I look at the weather in the middle of winter here. But at the Beverly Hills water treatment plant, we were seeing slightly elevated H2S due to bacterial activity in the groundwater that was being sourced to treat the drinking water. So in other words, Beverly Hills was reliant on the canal system and surface water for much of its water needs. But the irrigation district basically, or the water district, subsidized a water treatment plant so that Beverly Hills could draw groundwater and reduce its reliance on the canal water and aqueduct water. And so in that application, we went to a simple scrubbing tower, pretty compact tower, to basically take the water from the backwashed filter water from our sand filters at the start of the operation and scrub that. What was interesting in Beverly Hills is that this water treatment plant was located in the middle of their office building. So in other words, we had a need to treat levels of H2S inside a water treatment plant that was also showpiece as part of their office building. And so it required a system that was quite robust and could not be defeated or fail. I mentioned earlier the Horn River treatment plant for treating flowback and making water available for recycle. What we were successful in doing is working and connecting with some of the original designers of Horn River and trying to figure out, okay, how could we downsize the processes that were proven in Horn River and put them into a modular application. And so it's an example of Horn River was both the physical and chemical treatment. Likewise, even at the modular level, we're able to treat the H2S in water using a combination of physical processes, which would be similar to flash vessels, in addition to chemical polishing. So there's a variety of technologies that are available, and it really depends again on quantity, chemistry, and ultimate performance targets. For detection, many of you may spend your day with a portable monitor on your person as you go about your daily tasks. So there's a variety of detection methods that really also depend on what's the risk of a release that is at a very harmful level, and how quickly do you need to react to that release, and what information do you need in order to take prevent or corrective action. So we have everything from gas detection tubes, the gas tech or Draeger tubes that some of you may have used over the years, passive sampler badges, electrochemical devices. I know in sewer applications, the Odalog device and various logging devices are pretty extensively used. And then when you get into more fixed applications like plant environment in which you're expecting or you have a risk of ongoing exposure, you can go to a variety of real-time systems and logging systems, everything all the way up to open path laser system. So you have a variety of detection methods available to you. So as we start to think about closing this up, and I think, Joe, I think that you wanted to see about 40 minutes or so. So we're just about to the end of the journey on H2S. There's a number of factors, of course, that come into have we being duly diligent in the workplace in addressing this issue and the risk to the public and to our workers or to infrastructure. Obviously, H2S Alive training, and not just for those that are directly exposed on a daily basis, but those that may be in environments and inadvertently exposed to H2S. H2S Alive training is very critical. And I would say supplement it with a briefing with your team around what are the potential sources of H2S, what are the types of upset conditions that could alter the risk of exposure. Secondly, make sure there's engineering controls in place. So if you do an assessment of the source and the generation of H2S and understand whether or not that could be controlled or mitigated by engineering controls that prevent the release or prevent the downstream discharge. Make sure there's appropriate detection equipment in place as well. And that can be both at the personal level as well as at the more facility level. And then finally, make sure that there's appropriate personal protective equipment available for the staff. And a big part of that really relates back to almost detection equipment and having the right monitor system available as your staff are potentially exposed to H2S. So some of the lessons learned as I've looked through some of the case studies over the years, make sure you have a good understanding of what conditions that can generate that H2S in the first place and how changes in water chemistry, whether it's pH or temperature or turbulence or co-mingling with another flow, understand how those can impact the availability of H2S to be released from water. Understand how airflow can impact it. And so in certain environments where you have negative or positive pressure in buildings, in mine applications where you have multiple points of entry for air within a mine complex or system, understand how those fluctuate with time and can alter the risk of H2S exposure. Make sure you address the root causes of the potential problems with engineering controls. So often certainly in a refinery or natural gas processing environment, hazard and operability study is often used to assess the effectiveness of controls in certain situations. But there are a variety of tools that can be used to make sure that you understand what are the potential sources, what are the changes that could impact the availability of H2S, and how can we prevent the occurrence with reasonable engineering controls. Ensure there's protective treatment capacity and sufficient capacity to deal with any upset conditions. Remember that there are a variety of conditions that can affect the availability of H2S and how can downstream conditions change and therefore change the availability of the H2S. So be it a surge condition or co-blending with another flow at a different pH and a different turbulence, and understand how the combination of flows can be reacted to. Making sure there's personal monitors in place where there is a risk of exposure, and understand that detection, even at low levels, is a serious issue. So make sure that if you have your workers understanding that if you detect it at certain levels, then it's already a circumstance in which if you haven't done the other steps properly, creates a circumstance that you need to investigate more. So Joe, I think I'll close that off. It's been a little bit of a whirlwind tour through kind of the sources, some of the factors around treatment and availability, and some of the due diligence around it. But I felt it was really important to give this team on the phone call a refresher on the issues around H2S. Because as we know, the most important thing to do on any day of work is to get home to family, friends, and loved ones, and making sure that we manage the H2S issues are a key part of that, especially in Western Canada.
First question for you, Bill, or not? Municipal bylaws often have a limit on sulfides in water, but at the same time prohibit H2S from being discharged. Why is there restriction on some forms of sulfide and a prohibition on others?
That's a good question, because what you'll see in most bylaws is sulfides are dealt with in at least two different places, either a prohibition or restriction. So the restriction is really making sure that the amount of sulfide inside the water that's being discharged is kept to a minimum, because that sulfide is available to downstream bugs and bacteria that might digest it and generate H2S. So you have a restriction to keep the level low. So that's the restriction. The prohibition is H2S is bad in any case, and it's especially bad in the headspace where a worker might be exposed. And so really there's two levels of controls. Basically, restriction to make sure that there's not a quantity of sulfide available for the processes that are being implemented or used inside the sewer. And then secondly, the prohibition is protective of human health and infrastructure.
Good. Any other questions for Bill, please? Anything else you want to add, Bill, while I wait a minute or two to see if there's any other questions?
I think that, Joe, I think we've been, if you look at the incidence of H2S fatalities and poisoning as a result of the emphasis on H2S alive, I think we've seen a reduction in the incidence over the years. And really my goal, Joe, was to make sure that we did not become complacent about where it can continue to be generated. So for example, I have municipal clients that I've dealt with that find H2S is generated underneath the ice cover in storm ponds over the middle of winter.
Mm-hmm.
Some of the testing that we've done in storm ponds shows that the dissolved oxygen level near the bottom of a storm pond can kick into anaerobic digestion territory. So in other words, the dissolved oxygen is so low that the bacteria at the bottom of a storm pond are starting to digest any of the sulfates that came in with the stormwater runoff, release H2S, and it accumulates under the ice cover. So that's an example of you don't want to be complacent about where it could occur. And so when the ice cover comes off, yes, it's smelly. But of course, that may not be at that point at a specific location, may not be the place that I am drilling through that ice cover and doing ice fishing, for example. So it's a little bit of it may be a slight stretch to see that scenario turn into a fatality, but it certainly is an example of where an H2S generation under storm pond ice cover will lead to an odor problem or an odor complaint sometime in the spring.
Great. Yeah, it's a great reminder to people to always be aware of situations like that, especially with H2S. I think that's it that was the only question I received, Bill. So thank you again for doing this today, and thank you to our webinar series sponsor Site.